Yeah, sure. Yeah. Just go down. Yeah. So this is easily answered. Locally, it's one more time. Oh, like. No, I'm just like, I'll probably. I mean, I'll have it. It's done. Yeah, I think about it. Yeah. It was like $250.
If one,
They just make up size. Some turning matrix bulbs.
that's it.
Yeah, so if you're a user, all you have.
Then I can still use this method with the values.
Yeah, that's what I'm doing right now. That's the same thing. Because they have to go through each.
Yeah, he said this copy paste one time.
Well, this is an arbitrary size. So like my whiteboard, and I can just create this
Saturday, so long.
instead of
What's
having
that?
to write.
We're
there are-
Oh, yes, okay.
Yeah, no, I'm thinking of the board this Thursday, maybe even today.
Just to check. And see.
Yeah, no, how much is it? $60. $60. You off for those. Yeah, that's 130. 8 No, 882. She says it's 60.
This is perfect. This board is- I see the. Bring it back to the message.
Yeah.
I just gave her my phone number.
There are certain conditions.
Because
Like, I think that happened to me once, 'cause I suggested.
I think I'll give the other one is already for about that. I was gonna ask you one that's not sure. Putting the beach.
Hey Jerry, how's it going?
Pretty good. Sorry I couldn't make it to the in-person sessions. I did go online.
Oh, okay, no problem. I mean, I don't even look and see who's out there. So. I was good. It was very hot. I'm sure everyone else experienced that too. Over yours. Mm.
I got homework. Yours wasn't too hard. Thank you. Thank you for that.
That's good. That's good.
Have you ever done any research into underactuated joints?
Wait a second.
Have you ever done any research into underactuated joints?
No, I haven't.
No? Because we're doing research for that right now. Time over?
Uh-huh.
I know, it's like, I guess it's like, it falls under biomechanics, it's kind of simulating like the underactuation of your joints and fingers.
Oh, that's what you mean. Oh, yeah. Okay. Yeah. I mean, I haven't done any. I mean, I know it. I just know what it is. But that's it though.
You have one ligament going, or you have one, what is it, tendon? The one that pulls your finger down. What's it
Yeah.
called?
It's a tendon.
Yeah, so
Yeah.
you pull, so you have one that pulls it down, but it just so happens that you have two links here.
Yeah.
Underactuated, so they just happen to grip onto it too.
Yeah,
Just adds
yeah.
more grip.
Yeah.
So we're doing that right now.
See progress, but not.
It's gonna be the matrix.
Honestly, I was lazy to add the recipe, so I just eat whatever. So I just scan barcodes, or I just. You're joking. Wait, what is there? Oh no! You kidding me? Yeah. There's other apps too. Bro, look, that still works.
Oh my God, that's why.
Yeah.
Yeah.
There's another app actually. There's a change. That's on my students. Actually, is actually pretty helpful.
No, I guess I don't reply.
Oh, yeah. Today.
He's a really good friend.
That's all that matters. That's all that matters.
Oh, I understand that. Should we stay up then? There, oh my God.
Are you moving to do this? Are you doing it as a test?
All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good, all right. All right, so we're continuing right along, and so today we're gonna pick up where we left off last Thursday, and so we're gonna continue talking about muscle biomechanics. And so I'm thinking we're probably gonna finish that up today. And then after that, we're going to talk about joints. And so, kind of this trio of tissues, bones, muscles, and joints kind of form the, I would say the majority of the big biology part of this class. And so, kind of once we're done talking about, all these different soft tissues within the human body, we'll be ready to actually start doing some computations next week, starting with static biomechanical analysis. Okay. All right, and so announcements. So homework 1, I believe, is due Thursday, and so you can either bring the homework in and turn it in person in class, or you can upload the PDF onto Canvas. I think for this particular homework, because it's all short answer questions, I think what a lot of people have asked me is, can you type it up on like a Word document and then upload that Word document, and that's totally fine. And so I expect most people will do that. But if you did write it down on paper, you can turn it in. So either is fine with me. Okay? Whatever you feel most comfortable with. Okay, and so that's all my announcements. So are there any questions I can answer before we get started today? Okay, all right. So let's go ahead and pick up where we left off. And so last time we were here, we were talking about muscles and motor groups and how they're all activated. And so, where we're going to go from here is we're going to kind of, go, we've kind of started at kind of the micro scale for the muscles. We talked about, the protein filaments, how they interact. And so now we're going to go kind of at the fiber level and talk about the geometry of muscle fibers and how that works. And so we're going to start with fiber arrangement, muscle fiber arrangement. And so last time, we talked about how, the way that muscles can produce force or produce tension is that you have these tiny little, protein filaments inside the muscle fibers, and they kind of pull on each other, right? And so in total, basically, what you have are these muscle fibers that run through the muscle, right? And so here is a muscle, right? So here are these muscle fibers, okay? And what we saw was the way that force is developed is that each of these fibers, right? Each of these fibers can kind of pull on itself, right? And so it can basically become shorter, and as the muscle fibers shorten themselves, then they generate force. Okay? right? And so, when you're talking about muscles and the forces that they can generate, it's all kind of based on the fibers, okay? But, what's interesting is that, the way the fibers are actually arranged in every single muscle is different. And the way that the fibers are arranged basically determines, how much useful force or how much torque the muscles can actually produce. And so I put useful force in quotes because, it's not that any force is that the muscle can produce is useless. It's just that there's only a certain percentage of it that actually goes towards moving your limb. Okay. Right. And so, to kind of illustrate this, let me go ahead and introduce kind of the two kind of broad categories for how fibers can be arranged in a muscle. And so the first category is called parallel. And in a lot of, I think, visual renditions of how muscles look like, most tend to look like this, okay? And so in these types of muscles, you have something that looks like this. Where the fibers kind of all run this way. So in the parallel arrangement, the reason it gets its name is that the fibers here, they kind of run parallel to, what I consider to be kind of the longitudinal axis of the muscle. And the reason I kind of drew the muscle like this, with kind of the top and bottom, shortened, because usually over here, what you have is a tendon. Here you have a tendon, right? And if you remember from last time, tendons are these tissues that attach the muscles to the bones. And so, basically this muscle is attaching to the bone on top and attaching to the bone on the top, okay? And so in a parallel arrangement, when the fibers shorten, this entire muscle just becomes shortened and, and the bones directly come closer together. And when the tendons and the limbs are brought closer together, that's basically human movement right there, right? And so human movement, the way that we define it is when, your limbs are moving closer or further apart, okay? And so in this particular case, 100% of the muscle force is used to move the human limbs, okay? And so some examples of parallel arranged muscles will be the muscles in your arms. And so on both sides, and so you have both the biceps and the triceps muscles. And so I think those are kind of textbook parallel muscles where the fibers run parallel to the, not only parallel to the muscle, but parallel to the limb as well. Okay. And so those are, pretty, I think what people kind of draw first when they're asked to draw a muscle. Okay? But you also have a lot of muscles in your body that don't work like that. And so the other category of muscle, which are more broad, are called pennate muscles. Okay? And so the kind of the defining characteristic for pennate muscles is that the fibers are arranged kind of at an angle, right? And so there's lots of different examples of this in the body, but I'm going to draw one that kind of makes this distinction clear. Okay. So it kind of has this like lily pad kind of shape, at least in this kind of fictional pennate muscle. Okay. And the fibers, they kind of run this way like this. So it almost looks like maybe not a lily pad, but a leaf. Okay. There's a, for those of you who know me before, my wife is a graphic designer. And so there's a lot of my lecture notes for this class and other ones have to draw pictures. And it's always a running joke, whenever I try to draw something and she makes fun of me for it. And so she was watching me draw these notes and she's like, that's the ugliest leaf I've ever seen. I'm like, it's not a leaf, it's a muscle. And she's like, that's the ugliest muscle I've ever seen. Okay. And so what happens in these pennate muscles? And so, in the pennate muscles, just like in the parallel ones, when the muscle contracts, the fibers are going to want to shorten. Okay? Okay. And so that's still going to happen. And so even when they're arranged like this, okay. But you can see here that the action of the fiber shortening is going to cause a different kind of motion, okay? Because when these fibers shorten, right, what that does, if you kind of look at this kind of wedge that I drew in the middle right here, right? So you can see all the fibers are kind of attached to this wedge. And so as the fibers kind of shorten, and so, they're going to want to pull this way, right? This is the difficult thing about lecturing on the iPad is that I want to make motions with my hands, but you guys can't see them. Okay. Okay. And so as the fibers kind of pull in that direction right there, the net effect is that this wedge here is going to move upwards. Right? That's kind of the motion that's produced by this muscle. Okay. And then the fibers kind of become more flat. Okay. And so they kind of together kind of push this wedge upwards. And so kind of the net result of that is, this wedge kind of moves up and then these fibers kind of get more flat, kind of like this. Okay. And then this wedge right here is what attaches to the bone. And so this wedge here is usually connected to a tendon, and that tendon connects to a bone, and that's how you get movement in these pennate muscles. And so, probably what you can guess is that, in this kind of arrangement right here, not all of the muscle force actually goes towards moving the tendon. because the tendon motion here in this kind of theoretical example is purely up and down, right? It's purely in the y direction. And so it goes to, it kind of follows from that logic that the only component of the muscle force that actually goes towards moving the tendon is going to be in that vertical direction. Okay? And so, here's kind of a bigger view of that. And so let's say that we have a fiber whose total muscle force, is given in that direction like that, okay? But because force is a vector quantity, we can break this up into, its x and y components. And so we have the x component here, and we have the y component right here. Okay. Where just so that I'm consistent with my equations, this is the angle. And so we're going to find that angle to be right there. And I'll show you why I chose the angle right there anyway. Okay. Okay. And so in this situation, only the y component, only this one is actually going to go towards moving the muscle, or excuse me, moving the tendon. And so we can use a simple kind of trigonometric formula here to compute what that force is. Okay? And so if we say Ft, for Ft right here, this is the force that's put on the tendon. Okay? This is going to be equal to Fm. Fm being the total amount of tension that the muscle can produce. Okay, so that's just the raw force that when the fibers kind of pull together, that's what they can produce. Okay. And then you have this trigonometric factor here that accounts for the different directions. Okay. And so, with the angle up here, then that component there is going to be cosine of theta. Okay. And traditionally, that's kind of how it's defined. And so, traditionally, this equation is defined in terms of cosine. And so that's why I put that angle right there. And this angle, this is something that we're going to return to later on in different parts of the class. So this angle right here is called the pennation angle. And so it defines the degree to which, the muscle is pennated and how much of the muscle force actually goes towards moving the tendons. Okay. Okay. Question?
Oh, yeah. Do you have any examples of innate muscles?
Yeah, so your pectoral muscles are kind of the prime example of a pain. So, yeah. And so your pectoral muscles, they actually attach multiple places, but the degree of their pennation is a big part of how they move. Yeah. Mm-hmm. Yep.
Sorry, can you go back to the still fully understand about how the tendon attaches to the wedge for the
Yeah. So think of this as the tendon. So your limb basically is attached kind of on top of this muscle. And so imagine put your hand on top of that pennate muscle right there. And so as the pennate muscle kind of contracts, that wedge right there is going to move up and down. And so then your hand is going to move kind of up and down with it. Yeah.
So confused. So where is it?
The tendon is this entire wedge right, and the bone kind of attaches on top of that. Yeah. So actually, your deltoid muscle is another. The muscle in your shoulder is another good example of that too. Yeah. And so in that case, the deltoid, kind of wraps on top of your shoulder and then attaches to the bones that's kind of right underneath that.
So where the parallel muscle kind of stretches it.
Is
that my thinking correctly?
It doesn't stretch it. It just kind of moves it under. it's the pennate muscles are mostly muscles that that move limb that it sits on top. And so your shoulder joint is a good example because your shoulder muscle kind of wraps all around your shoulder, but it moves the arm, which is right underneath it. And so it attaches kind of your underneath that muscle quite a bit. So to move the arm, you know, that's how it kind of moves.
Gotcha.
Yeah. Mhm. Right. Any other questions on this? Okay. All right. And so, you know, the pennation angle for muscles that are pennated, you know, they vary, of course, muscle to muscle, depending on the function. But they also vary person to person as well. And so, you know, two different people, you know, you might see more degree of pennation than other people, which explains, you know, why some people will have an easier time doing certain tasks than others, because, you know, their anatomy is literally different. Okay. All right. And so now let's go ahead and talk about muscle function. Okay. And so, you know, there's another factor here that determines, you know, how much of the muscle force actually goes into moving your limbs, and that's kind of where the muscle attaches. And so I think, Pablo, this will kind of answer some more of your questions. And so, you know, we've already established that when a muscle contracts, you know, it's going to produce a tensile force, and a tension, as we know, is a linear force. Okay? And so when a muscle, you know, let's say that we have a muscle fiber here, okay? And so when it contracts, it's going to produce a tensile force that kind of shortens the muscle, just like that, okay? But that tensile force, you know, the way it actually interacts with your body is that it pulls, you know, on the tendons in your body, and those tendons attach to the bone, right? And the way human movement is designed is, you know, you don't really have a lot of linear motion in your body, but what you do have is a lot of rotational motions, okay? And so a lot And usually, you know, when we're you know, describing motion, we use the joints as a point of reference. And so, you know, for example, let's say when your arm is moving, you know, let's say you kind of move your arm up and down like this. What we say is that the arm is rotating about the shoulder joint. Okay? And so that means that, you know, when the muscles actually produce movement, like, yes, they're actually producing a tensile force, but then that tensile force gets converted into a moment about a particular joint. We can describe it as that it's producing torques. Okay. Right. And so a lot of times, you know, when we're talking about movement, you know, actually what we're interested in is the torques. Okay. And so, you know, the muscle forces, yes, are important, but then, you know, determining how much torque they produce about the joint. That's what's actually going to produce rotation. Okay. And so I'm going to draw an example for you. A very simple example in your arm. Okay. And so your arm consists of your upper arm. And here we have your elbow joint. And we have your lower arm. Here we have your wrist. Okay. And let's consider a situation where someone is holding an object in their hand. So, you're holding, a ball, a weight, something. Right, and so if we draw the free body diagram, we're seeing that the weight is going to be pushing downwards. Okay? I know it's an ugly hand, but apparently drawing hands is difficult for artists too. So I'm not the only one. Okay, and so let's consider two opposing muscles. And so we're going to consider two muscles in your upper arm that produce opposite motions. Okay. And so first one we're going to consider is the biceps. Okay. So your biceps. Patches kind of like that. Okay, and we have the fibers here. And let's also consider your triceps. And so your triceps are going to wrap kind of around the arm. This, and they kind of attach at the bottom of the arm. Okay. Oops. Can't spell joint. Right. So we'll ignore the wrist joint for now, and so we'll consider the wrist joint. We'll assume that the wrist joint is fixed, and we'll only consider motion around the elbow joint. Okay. And so if we have motion around the elbow joint, the arm can go either one of two ways, at least in this 2D plane, right? And so if the biceps are contracting, and so if the bicep contracts, okay, it's going to produce a force that's going to be in this direction. And so if the biceps contracts and that biceps gets shorter, right, it's going to cause the lower arm and the wrist to rotate. It's going to rotate in the counterclockwise direction, right? So you can kind of just imagine that, in your seats. But if the triceps are going to contract, right, so the triceps get shorter, then it's going to rotate the arm in the other direction. And so, we're going to have clockwise motion in that case. Okay. And so as we start to get, into the kind of the calculations and the quantitative part in this class, you'll hear me talk a lot about torques and moments and making sure they either sum up to zero, or once we get into dynamics, we'll get into angular accelerations and things like that. Okay. And so the torques and what they can produce is going to be very, very important. I don't want to get too much into it now, just because we're going to be spending weeks doing this. But whenever you compute a torque, the way that you compute a torque is it's basically the product of a force and a distance. right? So that's kind of the basic formula for torque, right? And so in this particular case, the force that's going to produce the torque is obviously going to be produced by the muscle, okay? So we've talked a lot about that. But what about this distance, right? And so remember, the distance in this formula here is defined as the distance between, where the force is acting and, the point of rotation. And in this particular case, our reference points are always going to be the joints. And so when we talk about distance here, and another name for this is going to be moment arm. Okay. And so the moment arm that we're going to consider is just the distance between where the muscle attaches and the corresponding joint. And so what you'll see later on is that there will be muscles that can produce a lot of force just because they're very big and bulky, but they may not have a very large moment arm. And so the amount of tension that they can actually, or the amount of torque they can actually produce is actually quite limited. And then you're going to see muscles in the opposite case too as well. And so muscles that may not be able to produce a lot of force, but because their moment arm is very large, they actually contribute a lot to to muscle or to limb movement. All right, any questions on this? Okay, so next let's go ahead and talk about characterizing contraction. Okay. And so depending on what the muscle is doing relative to, how the limb itself is moving, we can characterize how that muscle contraction is going, okay? Okay. And so there's three different types of contraction that we're going to talk about. And so the first one is concentric. And so concentric contraction happens when the muscle contraction, or the primary muscle that's acting is acting in the same direction as the movement. Okay. And so if the primary muscle is contracting in the same direction of movement, the net result of this is that the primary muscle is going to shorten in length. Okay. So an example of this is, just go ahead and take your hand and then just kind of rotate bring up your hand close to your shoulder. Okay. And so that action of bringing your hand closer to your shoulder, the primary muscle in that case is your biceps, right? Your biceps are acting to flex at your elbow. Okay. And so in that particular case, then we say the biceps are rotating concentrically. Okay. Because the biceps are shortening your biceps are firing, they're contracting, and it's actually shortening and bringing your hand closer to your elbow, or your shoulder, excuse me. So concentrically means that the muscle, the primary muscle is shortening. The second type of contraction that we'll go over is isometric. Okay, and so in isometric contraction, your muscle, your primary muscle is producing tension. Okay, and so it's actually trying to produce force, but all the resistive forces, all the forces that's opposing that motion are equal. And so even though the muscle is producing force, no motion or no rotation is happening. And so, maybe some of you have heard, the type of exercise that you do called isometric exercise, right? And so, in those kind of exercises, you kind of hold, a lot of them involve, holding a position for a long period of time. I think one good example of this would be a plank. And so if you want to work out your abs, what you can do is you can kind of, go on the ground, kind of lay on your elbows and kind of hold that as much as possible. So even though your body isn't moving, your abs are still, contracting to try to keep you holding you in that position. And so that's a good way. It's a good way to exercise, without moving your body. Okay. All right. And so the third type of muscle contraction I will go over is called eccentric. And probably by process of elimination, you can probably tell what this is. And so in eccentric contraction, your primary muscle is trying to contract and produce tension. Okay. But the motion this time is going in the opposite direction. Okay. Right, so I remember, when I was in high school, I played soccer, and my coach was a police officer. And so what he would always tell us whenever we were working with weights is that, let's take a bicep curl for example, right? And so he would say, bring the weight up as quickly as you can, but when you're letting it down for the next rep, go as slow, try to let it down as slowly as possible. Okay. And so in that case, your elbow is actually extending, right? And so your bicep, naturally wants to pull your arm up towards your shoulder. But in that case, you're letting it fall down. But in that case, you're not just letting the weight just free fall. You're trying to let it down as slowly as possible, so that even when you're letting it down, you're still giving your biceps a workout. And so any situation where you're using a muscle to kind of act as a brake or to kind of slow down a particular motion, that's called eccentric contraction. All right, and so those are the three types of contractions. So depending on what the motion is doing compared to what the muscle is doing, we can characterize that muscle contraction as either concentric, isometric, or eccentric. Okay. All right, any questions on this? Okay. All right, and so before we move on, what I want to remind you, and the reason I drew two muscles here is that a lot of muscles in your body actually act in pairs. Okay, and so usually when one muscle is acting one way, the other muscle is doing the opposite, right? And so take the bicep curl for instance, right? And so when you're pulling up your arm here to a bicep curl, your biceps are acting concentrically because it's going along with the motion, but at the same time, your triceps aren't just sitting there doing nothing. So it may seem like they're not being engaged much, but they are contracting a little bit, mostly to act as a brake, right? To kind of control that motion so that you don't like whip the weight kind of up and smack yourself in the face, okay? And so in that case, your triceps there are acting eccentrically. And so, even very simple tasks that you may think maybe only one or two muscles are required, actually, a lot of muscles in your body are kind of working together to make sure that task is accomplished. Okay? Because otherwise, if you have just one muscle acting at any given time, you'd be surprised your muscles would actually act pretty erratically. And so, the opposing muscle or the partner muscle or the pair, whatever you want to call it, plays an important role in making sure that your movements are controlled and they do what you want them to do. All right, any questions on this? Let's see, what else do I want to talk about with muscles? Okay, all right, so this is important. And so kind of building off this point of concentric, isometric, and eccentric, we can actually, characterize the amount of force that your muscle is actually generating based on the velocity of the motion. Okay? So the magnitude of the tensile force produced by the muscle actually depends very strongly on how quickly the muscle is shortening. Okay. And so generally speaking, the faster your muscle is moving, the less force it can actually generate. Okay. And so if you kind of move your muscles really quickly, in those situations, your muscles actually can't produce that much force. Okay. And the reason for this is actually not so bad to understand. Okay. Because remember what we talked about last Thursday, and that the way that your muscles actually generate force is that you have these protein filaments inside your muscle. And they have these filaments that actually pull the muscle towards each other. Right? And so I'm going to draw just one example here. Okay, so inside your muscle fibers, you have something that looks like this. Okay. Right, and so we have these myosin heads. Okay. And so when the muscle contracts, we know that these heads are going to attach to the actin here. Okay. And they're going to pull it this way. Right. And so by pulling it that way, it generates force. Okay. But if the muscle wanted to produce even more action in that direction, what the heads need to do is that they need to detach from where they were before, rotate back, attach again, and then pull it forward. Okay, so it's like a set of guys kind of rowing a boat. Okay, and so before they can kind of do a forward stroke, they have to kind of rotate back. Okay, so to keep yeah, I know I was talking about that pretty quickly. Yeah, let me write it down first, and then I'll go. So I think the easiest way is to kind of do this kind of visually. Okay. And so if we call this kind of position one, right? And so in position one right here, the myosin heads are kind of rotated, in a way where when they pull, right? When they pull, they kind of pull this actin filament kind of closer together. Okay. And so after position one, the situation is going to look like this. Okay. And so after the myosin heads kind of attach to the actin filaments, they rotate to kind of pull that over, right? And so now they're going to be oriented like this, where they kind of pull towards the middle. Okay. But let's say that we're in a situation where we want to keep contracting, right? And so this contracting here is not enough. And so in order to prepare for the next contraction, these myosin heads have to rotate back. Okay? And so what they're going to do here is that they're going to detach from the actin head. Okay. Right. And so when they detach, they won't be able to, they're not attached to the actin anymore. Okay. And so now they're free to kind of move without actually, affecting the muscle. And so in step 4, they're going to rotate back to position 1 and reattach. Okay. Right. So think of like a rowboat, right? And so when you're rowing a boat, when you do a power stroke, the oars are in the water. So that's kind of the same thing as the myosin heads kind of pulling the actin closer together. Yeah, exactly. But to make sure that your boat's still going in the same direction, right? You kind of pull the oars out of the water, you rotate the oars back to a starting position, and you kind of rotate it just like that. And so actin and myosin kind of act just like the same way. And so the reason I'm bringing this up, and so I know I said that we weren't going to talk about this again today, but the reason I'm bringing this up is that this whole process takes time. Okay, and so this process doesn't happen instantaneously. It takes time for the myosin heads to kind of detach, attach again, pull, detach, rotate, reattach, pull, and so that whole process takes time. Okay, and so the faster that your muscle is contracting, basically the less that your fibers here are able to attach well. Okay. Okay. And so if your brain is telling your muscles that you need to rotate really, really fast, it may not be able to do a full power stroke, or it may not be able to do a full rotation back. Okay? And so this whole process kind of gets sped up, and they're not able to kind of do this whole cycle. Okay. And so as a result, what we've seen is that we have this kind of inverse relationship between velocity, contraction velocity, and force. Okay. Okay. And it can all be summarized in a single graph. And so on the x-axis here, I'll have a contraction velocity. On the y-axis here, I'll have muscle force. Let me draw a dotted line on this graph. And so this dotted line will be zero velocity, okay? And so this line here is going to be the isometric line. Because remember, isometric contraction is when your muscles are producing tension, but no motion is occurring. Okay? And so there's a point on this line, which I'll denote with that dot right there, okay? And so this dot right here is known as the isometric maximum for the muscle. And so the isometric maximum is basically the theoretical maximum amount of force that the muscle can produce. And you can observe that when the muscle is contracting isometrically, okay? Right. And the reason that is because, when there's no motion, right? So all the myosin heads kind of have a perfect chance to kind of attach where it needs to, and you have kind of a full power stroke from all the muscle fibers within the muscle. Okay? But as the speed goes up, and so as you get into more concentric contraction, the amount of force that your muscle can produce actually goes down. Okay? And so it actually goes down according to something approximately equal to that. Okay. And so, of course, this exact curve is going to look different for every single muscle, but it kind of has that approximate shape. Okay.
Wait, Professor, do you mind explaining that again?
Yeah. And so basically the idea is that the faster your muscle is contracting in concentric contraction. Okay, so everything to the right of this dotted line here is going to be concentric. Concentric contraction, right? And so there's basically motion along the same direction as the muscle. The faster that that contraction is happening, the less force that your muscle can actually produce, because the motion is kind of too fast for your muscle fibers to attach kind of optimally. Right? It's something a bit different, and so fatigue is something a bit different. So fatigue is Fatigue is kind of more of an inability for muscles to act kind of after long repeated movements. But this is even if your muscle is kind of at full strength. And so even if there is no fatigue at all, the faster you contract the muscle, the less force that it can produce. Right? So think about, I keep coming back to kind of a dumbbell curl, just like I think it's the simplest one to do, right? If you have just like a little dinky, like 3-pound weight, you can kind of, shoot that thing up because it doesn't require that much force. But if instead you have like a 25, 30-pound weight, you can only do that. You can't do that fast because, you can't contract that fast and produce that amount of force at the same time. Mm-hmm. All right. And so of course, this curve, this plot here is only half complete. And so, we have the second half. And so the second half here, of course, is going to be eccentric contraction. So remember, eccentric contraction is happening when the muscle movement or the movement is opposite of muscle contraction. Okay. And so actually in eccentric contraction, the curve actually goes up. And so it actually kind of goes like that. Right? And so if the velocity is negative, and so negative velocity basically means that the movement is opposite of the muscle contraction. Okay, the amount of muscle force that you can actually produce actually goes up, okay? Which confuses everyone because the medical term for this one actually is isometric maximum, but it's not even a maximum of its own curve, and so it's a curve that kind of just keeps going. But the reason we call it the isometric maximum is that once you kind of get into eccentric territory, you're gaining some benefit from kind of the passive elastic components of the muscle. Okay. And so remember what we talked about last Thursday, or maybe it was last Tuesday. Muscle is an elastic tissue, and so if you stretch it beyond its resting length, it's going to want to return back to its original position. Okay, and so in eccentric contraction, that's happening because the muscle is doing everything it can to try to oppose that motion, but despite that, it's increasing in length. Okay, and as that muscle increases more and more in length, you're getting this passive elastic component that's actually trying to act in the same direction as the muscle force. Okay. So that last part there is kind of key because that's not always the case. And so normally, you think of your concentric contraction, right? And so you're doing a bicep curl, your bicep is acting concentrically and your muscle is shortening. Okay. When your muscle shortens, the passive elastic components are going to want to push it back out. Okay. And so in concentric contraction, you have kind of they're kind of opposite direction because your active muscle components want to shorten the muscle, but the elastic forces want to lengthen the muscle again because it wants to return to its original length. Okay? In eccentric contraction, the opposite is happening. And so, in eccentric contraction, the muscle itself is lengthening. And so as it's lengthened, the passive elastic components are going to want to shorten it again. But at the same time, your muscle is kind of fighting for its life, trying to shorten and produce tension to also, bring it back together. And so, eccentric contraction is kind of when those two forces kind of act in the same direction. So that's why you get kind of a boost. Okay. And so kind of a way to kind of augment this graph right here to make it a little bit easier to interpret, right? We can draw kind of a third line right here. Let me use a different color actually. And so in eccentric contraction, your muscle itself cannot actively produce any more force. Okay. So this green right here is the active force component. So when you're going to the eccentric territory, the active component is actually not going up anymore. So it's stuck at that isometric maximum. But the total amount of force that your muscle is producing is going up because you're getting help from the elastic components as well. That's why they call it the isometric maximum, because that's the maximum amount of active force your muscle can produce. But you know, depending on if the muscle is shortening or lengthening, you get some help from the elastic components.
Professor,
Was there a question?
yeah, can you hear me?
Yes.
So the active force component, would that, like, for an example, would that be the weight that you're curling in a bicep because it's not changing?
Yeah. So what I mean by the active component is the effect directly from the protein filaments pulling on each other, right? And so, you know, when I talk about active components, that's when, you know, your brain sends a signal to your muscle, and that tells these actin filaments they need to pull or produce an active component, right? But even without any active component at all, so, you know, consider that you have a muscle at rest, right? That muscle at rest kind of by itself acts as like a rubber band, right? And so, you know, and you can test this out even in cadavers too, you know, where the muscles are not active at all. So if you try to stretch the muscle just by itself without any active components, it's going to want to return back to its original shape because it's an elastic solid. And so that's kind of what I mean by the difference between active and elastic components. And so if you look, I think if you look back at the beginning of the notes we did last Thursday, I drew kind of that. I drew this kind of figure right here, right? And so every muscle, you know, that has this active component. And so we've been talking primarily about this part right here today. Okay? But there's also the passive parts as well, which kind of act as like springs. And so your muscles have additional springs that kind of help with, you know, help with its motion. And that purely just comes from elastic forces. Okay. All right. Any other questions on this? All right, so we have about 10 minutes left. And so the last thing I want to talk about are just some common injuries that your muscles can sustain, and what's going on, you know, to your muscles at that time. So muscle injuries are quite common, and so you know, they happen to basically almost everybody. And so there's lots of different types of injuries your muscles can sustain. So the first one I'll go over is a strain. Okay. And so a strain is basically whenever you have muscle tissue in your body that gets damaged. Okay. And so that damage can occur either from overstretching or overloading the muscle. And so the degree of strain, there's a huge you know, range of different strains. And so, you know, a strain can be anything that's really, really minor that, you know, you may only be hurting for a day or two, but, you know, strain can also characterize almost a complete tear of the muscle as well. And so a strain is used, you know, anytime the muscle fibers or muscle cells are damaged themselves. Okay. And so to heal a strain, you know, your body itself can heal your muscles on their own. Okay. But they need to be given a chance to do so. And so the best kind of course of action to heal a strain is usually just rest. And you can put some ice to lower the inflammation, but usually rest is kind of the best way to do it. Okay. But resting can get kind of tricky too, because, you know, when I say rest, you know, you really have to try to minimize that amount of muscle activity as possible. Right? Depending on where you get the strain, that can be very, very difficult. And so a lot of people get strains in their lower body. So it's very common in your hamstrings. It's common in the groin area for some people. Okay. But, you know, just a natural consequence of just moving around on Earth with gravity, you know, it's very hard to, you know, unless you're just going to sit in bed totally prone, you know, it's very hard to, you know, have any kind of movement and not aggravate that strain. And so, you know, some areas of the body are, you know, they get the reputation that it takes longer for strains to heal in certain areas, just because certain areas of your body are very difficult to rest, you know, without, you know, literally kind of immobilizing yourself. Okay. Number two, the next injury is a contusion. And so contusion is another name for a bruise. And so I think that's what people generally know them as. And so contusion happens when the muscle suffers a compressive force, a large compressive force, usually from an impact of some kind. And so what's happening with the bruise is that, you know, that impact or that compressive force was so large that it causes a rupture of some internal blood vessels inside the muscle. And it causes some localized internal bleeding in the muscle. Okay. If you ever had a buddy kind of punch you in the arm for your birthday, you probably know what a contusion is. We don't play that game I don't play that game with my friends anymore because we're getting old, and, you know, 31 punches is hard to take the arm at this age. All right, and the last one we'll go over is a cramp. Okay, so everyone's probably experienced a cramp at some point. And so there's you know, there's a lot of research being done on cramps and what causes them and what's the best way to treat them. The result of all that research is still kind of inconclusive. And so at this point, you know, we don't have a definitive answer for what causes cramps, but we do know that it's really painful when they happen. And so some of the causes that have been, you know, that people kind of generally talk about in the research is that people think that cramps are caused by electrolyte imbalance. And so, usually if you're cramping, people are always going to tell you to drink water or drink Gatorade, to try to restore that electrolyte balance. Okay. Or another theory that's out there is that some kind of deficiency in kind of the chemical processes within the muscle. And so deficiencies in essential minerals like calcium and magnesium inside the muscle. And so minerals like that are actually really important for that cross bridging action. Okay. And so when the myosin head's attached to, or first of all, when they receive the signal from the brain to detach and detach, right, it needs calcium and magnesium to do that. And it's a big part of the control sequence. And so, when you have deficiencies in there, people think that it causes, that's, part of the contributing factor towards. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all the time we have for today. And so thank you everyone for tuning in. Thank you for coming today. And so on Thursday, we'll finish up the tissue series with joints. Okay? So have a great day, everyone. Everyone stay warm. I mean, stay cool. Stay cool. It's way too warm outside right now. So, make sure you're hydrated. Make sure, you're not out in the sun too much. Take care of yourselves, and I'll see you guys on Thursday. Anthony, any final questions? Okay, all right. So I'm gonna go ahead and close the call. See you Thursday.